Thank you, Kevin. My name is Simon, as he said. I work as an infrastructure lead at a company called Shopify, based out of Canada. Shopify, just as a way of introduction, is a company that powers a fairly large amount of online commerce, actually both here in Scandinavia, but also in North America. So if you bought something that's not been on Amazon, there's a good probability that you may have been through a Shopify store and used some of the infrastructure that we're going to talk about today. The talk today is going to be fairly high level, and I'm going to be give a fairly comprehensive overview of the architecture that we built at Shopify to support these very, very large sales that we see from some of the largest or biggest American celebrities and some of the largest brands both in Europe and also in North America. So we're going to be talking about especially the architecture that we've evolved over the past 5 years, and we won't go super deep into any particular point, but rather give a comprehensive overview of all the different components, how they fit together, and hopefully inspire something that I think can be leveraged in a lot of other companies, especially SaaS companies that can have a similar architecture to ours. Come on. Clicker is having trouble. So Shopify is a company that helps people sell, both online and in many other places. And about 5 years ago, we faced a bit of a fork in the road. We were starting to see these customers that were sort of online first. When retailers went online about 7, 8, 10 years ago, often they'd had a physical presence and then moved online. But we were starting to see a lot more customers that started with an online presence. And they also started to require new ways of selling. With social media becoming very, very big over the past decade, and especially 5 years ago, smartphones were out in everyone's hands, and Instagram, Facebook, Twitter, and so on had become quite large. And this enabled new ways of selling online that people hadn't quite been able to do in the past. We call this a flash sale, and the idea of a flash sale is that you announce a product, sometimes minutes in advance, sometimes days in advance, sometimes hours in advance, that you're going to release some kind of exclusive product at this day and time. And as you can imagine, that can drive an astonishing amount of traffic to one site from just 1 minute to the other. It's 1 minute before noon, and everything is good, but at noon, you have hundreds of thousands of people coming in trying to buy some of the same products at the same time, placing an enormous strain on the system. You can imagine this from Super Bowl, Kylie Jenner, if some of you know her, famous for being famous. And she's out of the Kardashian family selling lipstick, and she can drive a very enormous amount of traffic, and Kanye can do that as well. So about 5 years ago, it was not these very large Super Bowls and things like that were starting to use this way of selling, but rather still customers that could drive a very enormous amount of traffic. And we were faced with a fork in the road. Do we become a company that tries to support these sales, or do we just tell them to go and find another platform, a platform that actually didn't exist, but it's a very hard thing to be profitable from. It takes thousands of engineering hours to be able to scale to these sales when you haven't architected for it from day one. We chose the path of trying to support these. We chose to see these sales as a way to identify bottlenecks and as a bit of a canary in the coal mine as to what is going to break next. The flash sales of today tell us something about what the traffic is going to look like 1 or 2 years from now. This was, wrong direction. This was such a powerful decision at the time and so important to our CEO, who's very technical, that he wrote an internal essay on why we support flash sales. This is really important in our company philosophy, that we want to, as in the face of adversity, become stronger and not weaker, or just not use it as an opportunity to grow. When something bad happens, we want to come out stronger. And he wrote an essay about why flash sales was such a case. We have a very strong culture internally of trying to inject chaos into various parts of the organization and try to come out stronger as a result. If you drop a piece of glass, it breaks. If you drop a rock, it's indifferent. But what can you drop that becomes stronger as a result? You know, if you go down to the gym, you run on the treadmill, you come back a couple of days later, and you can run further and faster. How can you build software in that way? And flash sales was such a thing for our organization. It was a way for our infrastructure to become stronger. Just a couple, before we get into the meat of the talk, and with this preface of how important flash sales have been to the history of our application, here's some of the numbers to keep in the back of your head for the scale that we're running at. We support about 500,000 merchants, paying merchants, all over the world. We processed almost $6 billion in the last quarter. We run up to 80,000 requests per second to our Ruby on Rails processes. We do about 40 deploys a day to this, and we have over 2,000 employees, a large fraction of those engineers deploying all the time. The mental model that I want you to incorporate for this talk is that we have about 3 different tiers that I'm going to talk about. We have the traffic tier with all the traffic coming in, and which is responsible for getting your requests from your home network all the way to our infrastructure serving back the page that you're requesting. We're going to be talking about the application and the data tier that work together to serve those pages. And we're going to be talking a bit about some of these arrows. How do we fail over between regions with 0 downtime? How do we shard our application, and how do we balance those shards as some shops grow bigger so that Kanye and Kylie are not on the same shard, but rather spread out? And how do we get from the traffic layer into the application layer and failover regions? How does all of this stuff work together? You should have a pretty good idea of how that works for us by the end of this talk. We're going to be starting by talking about the traffic tier. As I mentioned, the traffic tier to me is the layer that is responsible for how to get the request from A to B. In this case, from your home network to our network. We're going to be talking about how we do global routing, because this is something that we face a lot of debate with internally. We're going to be talking about a technology called OpenResty, which is absolutely incredible, but quite underused. We're going to be talking about how we protect ourselves from bots doing sales, how we serve cache hits from the load balancers instead of the application tier, orders of magnitudes faster, and how we throttle the checkouts doing very, very large sales. To understand how your request gets from the customer to our data centers, or regions as we call them, we need to understand a little bit about how the internet works. This is a very high-level overview of how the internet works and how the routes propagate. If you are Facebook or Google, and you have one domain and not a bunch of customers pointing their DNS to your domain, then you can do a lot of really complex traffic engineering at the DNS layer. But when you have about 1 million domains from 500,000 different customers pointing to your IP, you have very limited amount of control at the traffic level. You only have the IPs that the customers are pointing us to. You can't control anything at the DNS level. So we did something that hasn't had a lot of use in the industry. For those of you who know about networks, it's called BGP TCP Anycast. And I'll explain here how it works. How does traffic get from the customer to our regions with this TCP BGP Anycast? So what happens is that Shopify has IPs. As you can see here, we have this /24, this block of 255 IPs. And our regions will announce to the internet that these IPs can be routed by these regions. So if the ISP sees that IP, it should be routed to the Shopify region. So what Shopify will do is that we will connect our routers into our ISPs and say, hey, we own these IPs to our adjacent ISPs. So we may have, let's say, 2 ISPs that we connect directly to from our regions, and we tell them, if you encounter these IPs, send them to us because that is Shopify traffic for some Shopify store. Those ISPs then tell their adjacent neighbors, the ISPs that they're plugged into, that they can route those IPs and they know how to route them. And like that, it's propagating through this entire web. You can think of this as a bit of a gossip algorithm where every neighbor or every ISP is constantly telling its neighboring ISPs which IPs it knows how to route. This entire propagation to, you can imagine, ISPs ranging from Asia to Europe to America to South America of these IPs, that entire internet broadcast takes about 7 minutes, which is either amazing or very slow, depending on where you're coming from. So now we have this connected web. How does that customer then get their traffic to the region? Well, they make a request, right? So in this case, they're going to the Walrus store, and it's pointing to the Shopify-owned IP that is part of that block, that IP block that the regions are announcing. So it's going to our ISP, and then it either needs to turn left or right, depending on which region is closest to that ISP. In this case, we're going right, at least from where I'm standing, and the request is then routed to the region. This works really, really well for when you're pointing all these customer domains directly to IPs and you don't have too much control over it. So now we know how the traffic gets to Shopify. Now I want to talk a little bit about what happens when that request enters our network. We use a technology called OpenResty. OpenResty is perhaps one of the best additions we've done to our technology stack in the past 4 years. It enables you to script your load balancers, your Nginx load balancers, with Lua. You can do pretty much everything that you desire. You can customize your load balancing algorithm. You can redirect to other data centers. You can change the headers. You can inspect cookies. You can serve different content based on requests and cookies. You can do external networks. You can do all of this stuff, all in the comfort of inside of Nginx, which is extremely fast and extremely stable. I think OpenResty is quite underrated, and I don't hear quite enough talk about it because it is so stable, so fast, and so scalable. I want to talk about a couple of modules that we built with this. It really has become our hammer and nail to solve a lot of traffic-related issues. And we've gotten away with waiting off a lot of DDoSes and DOSes just from simple Lua modules. It's really powerful to be able to script your load balancing tier. And here's just a very quick example of what it looks like. This is a very bare bones Nginx config that is just listening on a port, and in this case, serving some content by Lua. And you can do all kinds of things here, right? You can do customized load balancing algorithms, like you can imagine doing network I/O in this block. You could do pretty much anything. So one of the modules I want to explain is that we have this big problem of bots. There is, surprisingly, as we learned, there is a very large secondary market for sneakers. So there's a lot of people out there, sneakerheads, and they collect sneakers. And to get these sneakers, you need to be there when the sale happens, and you need to be really lucky because there's limited inventory. Maybe there is 200,000 people competing for 5,000 pairs of shoes. When that happens, there's an economy here where you can buy these shoes, and if you buy them, you don't wear them, you sell them on eBay for maybe 2 times, 3 times, 4 times the price. Of course, merchants don't want that. They don't want secondhand markets charging more than they were and not controlling the customer experience. So they were asking us to come up with a way to detect these bots and ban them. So we took out our hammer and nail, OpenResty, and built some modules that helped us solve this problem. The Kafka logger module is one that we've had for a long time. Every single request that comes into Shopify is logged into Kafka, a distributed message bus, and all the messages there are relayed into our data warehouse. But we can also consume these messages in real time and make decisions about them. So you can imagine that there's a Kafka cluster here, and for a checkout, we log that checkout into Kafka. Then there's a stream aggregator, and this is the bot squasher. It listens on Kafka and tries to, in all of these different events, see whether there's a suspicious pattern. Is there something that doesn't look like a human? Is it refreshing a page very, very rapidly in a way that a human in a Chrome browser would never do? Or is there something else at stake? This is a fairly sophisticated algorithm to try to figure out what is going on. It is not an OpenResty module. It's just a simple consumer, I think written in Go in this case. And when it finds something, an IP or user agent or something else that looks like a bot, it can tell the rule banner, which is written in Nginx, and it's just a simple DSL that allows you to ban various patterns, very simple patterns like user agents, IPs, and the bot squasher can then, based on the assumptions made from the Kafka stream, ban an IP or something else with the rule banner on all the load balancers. Now we can reject these bots in a few microseconds, and people can write very sophisticated algorithms at the bot squashing layer to ban these bots very rapidly. When we deployed this, we saw a fairly sizable decrease in the amount of requests coming to Shopify. And we had to turn it off again because we were so flustered, like this was way too many. But it turns out that a very, very large fraction of our traffic was actually just bots. Another thing we do with OpenResty is that we serve cache hits. So we can, if you go and browse a Shopify product, there's probably someone else maybe browsing the same page or the same product later. So we can cache that if nothing changes. We can go to the application tier and serve that cache hit, which is stored in memcache, but we can do this orders of magnitude faster if we do it at the Nginx layer, just because of the overhead of the Ruby VM and the whole stack that we have there, which is very difficult to optimize at this point. So you can imagine a request coming in, it's getting some collection of filled with Walrus products, and you have a cache miss. You get to the web application tier, but when you're fulfilling that request, getting all the data from the data stores and rendering requests back to the user, we're also filling the request into the cache so someone else can serve it. Really, really simple stuff, nothing novel. But on the next hit, what can happen is that edge cache, which is an OpenResty module, will check the cache directly at the load balancing tier. This is fairly simple, right? So now we can get it directly from the cache, not even touching the application tier, making us able to handle orders of magnitude more requests per second with a fairly small addition to the stack. This is more complex than it looks, at least for our stack, because generating the cache keys and things like that has turned out to be quite complex. But for smaller applications, this might be quite simple. We don't have this turned on for everyone, but we do have this turned on for some larger merchants. And the reason why this is hard for us to turn on is that people on Shopify can customize their themes completely, and getting that to play very well with caching has turned out to be more difficult than we thought. The last one I want to talk about is the checkout throttle. Some merchants come in and can drive so much traffic that we can't handle the amount of writes that they can do on a checkout. And you can't cache a write, so you need to do something. At some point, there's so many writes going into the database for adding the checkout or running scripts that modify the cart, all these kinds of very complex operations that happen when you're checking out, getting shipping rates, processing payments, that we have to throttle it. Very few merchants ever hit this. I would say probably less than 10 or 20 unique merchants in the lifetime of Shopify have ever hit this throttle. But when it does happen, it's very important that all the shops that are on the same shard as you do not suffer under your sale. So what we do is that when a request comes in for a very busy store to the checkout, we will put that request into a queue, again, happening at the load balancing tier. Now, while you're in the queue, you're redirected to a wait area, which is completely customizable for the merchant. Again, we strive as hard as possible to not put people in this at all, but we need to have a safeguard in case it does happen. We control the rate at which we leak from the queue with a throttle, and then when the throttle is done, we will redirect you back to the checkout. So now we talked a little bit about the traffic tier, some of the OpenResty modules we do, and how traffic gets all the way to Shopify. Now I want to dig a bit into how does our application layer work and how does our data tier work. I'm going to talk about both of them at the same time because they're quite intermingled. A very important concept for us is what we call a pod. Some companies may call this a shard, but a shard to us means a MySQL, like a relational shard. A pod to us encompasses more. A pod to us is a small Shopify, small isolated Shopify that can run anywhere in the world. It can run in a cloud, it can run in a data center, it can run anywhere. So a pod is an isolated unit of Shopify that with one or more shops. You can look at it like this. If we have, let's say, pod 7, pod 2, and pod 14, they all have a bunch of shops on them. These shops don't talk to each other. The pods don't talk to each other. They're completely sharded and isolated from each other, giving us some very nice scaling capabilities. This is a fundamental isolation principle that we call the shop isolation principle. All shops must be isolated from each other. If you want to do something cross-shop, you have to use the data warehouse or some other mechanism. Because doing things across hundreds of shops, hundreds of pods in multiple regions is not something that's going to scale, at least to do in real time. So another thing I want you to note here is that these pods are not of the same size. Some have more shops than others, and we're going to address that problem later. But first, I want to look at what's in a pod. So a pod is one or more stores, but what does that mean? Well, it means that all the stateful layers of that pod are isolated. So a pod has a MySQL, it has a Memcache instance, it has Redis instances, and it has cron workers that are doing periodic work. So all the stateful data of all of these shops is shared between, or is isolated from all the other pods and all the other shops. Now, there is a tier that is shared, and those are the workers. So when a web request is handled or a job is handled, it's shared between the pods. Now, why is that? Why would that tier be shared? The reason is because of the sales. Remember, the preface of this is that we have to architect for these massive sales. And if pod 2 is experiencing a massive sale, some kind of launch, then they may need to be able to get perhaps 60 to 70% of all the worker capacity to handle that sale. So the stateless stuff is shared, and the stateful stuff is isolated by pod. Now, why wouldn't you have an autoscaler for this? This sounds like the canonical thing to solve with a cloud autoscaler, right? So when you have a sale, you just start spinning up more instances. The problem is that spinning up those instances is going to take tens of seconds. And during that time, you're going to be serving a lot of errors and have a very bad experience for all the customers coming in. So we don't do that. And maybe one day we can. Maybe we can do some really crazy things so that we can spin up these workers fast enough with an autoscaler. But today, it's not the case. Another stateless thing that is shared is the traffic tier that we talked about before, where all the OpenResty modules are running and the load balancing is happening. Another tool that I just want to introduce while we're here to test the stateless tier is that we have a load testing tool called Genghis. What Genghis does is that it runs Lua scripts that define a flow through our application and allow us to test with an astonishing amount of load using cloud instances what happens when we send, for example, 10,000 people per minute through the checkout. You can customize this as much as you want with Lua scripts that allow you to say things like, this customer is going to go to the product page, they're going to browse around a bit, they're going to be a little bit indecisive, then they're going to add some products, remove some products from the cart, check out the entire thing, and pay for it. And then you multiply that with maybe 10,000, 6,000. The interface to this is really simple. We have a Slack bot which just responds when you tell it to enqueue some Lua script. The JSON file here that you're enqueuing describes which Lua script to use, which store to target, how long to do it, and at what rate. How many of these executions do you want per minute? So remember that problem from before of all of these pods being of different sizes. This year, that's a problem that we've been trying to address. In the past, what we've done is that when we needed to provision a new pod because we've had too many shops, we replicated everything in that old pod that we wanted to split in half over to a new pod. Then, for a short duration of time, we would change the routing layer to have half the shops go to the new pod and the other half to the old pod, and then start cleaning up the old pod. It was a bit of a mess and a very operational manual amount of work. I think the checklist for doing this was like 100 items. So we wanted to make this better and less risky and have less like big hand-wavy movements to move all of these shops between shops with less downtime. So we wanted to be really, really good at moving shops between pods. And we wanted to see if we could do this with the smallest amount of downtime possible. We shouldn't punish large merchants such as a large Shopify store that may take hours to move and give them hours of downtime. Even if they can schedule it, that's a terrible experience for a merchant that maybe has an opportunity cost there of perhaps several $1 million that they're losing in that transition. So what the pod balancer does is that it looks at these pods and it looks at the shops. And then the pod balancer will make some decisions about how to balance these pods. So you can imagine in this case, it sees that pod 2 is a bit bigger, it moves some shops to pod 7. But in interim, pod 14 grew. One of these shops is occupying 3 shop units. This could be a shop that has large sales. It could be a shop that is very large. Maybe this is a shop that is re-platforming from another commerce solution and has grown tremendously in size. Some of these shops are bigger than others, just in terms of size, scale, sales, whatever they do. And the pod balancer just continues to work, right? So it moves some other shops from pod 14 over to some of the other pods. But the complexity increases because you also have signups. You have new shops coming in, and you have other shops growing. And the pod balancer just keeps working at it. The pod balancer keeps trying to fill up all these pods that are of equal size. Before we had this, we would have some pods that were maybe twice as big as others, giving you a bit of a noisy neighborhood problem where on some of these shards, you were experiencing more incidents than before. So what happens now when they're all filled up? Well, you create a new pod. And we're working this year on making that really easy, and the pod balancer simply making a decision to create a new pod and then moving the shops over. We want this to be something that is always on and something that we never have to touch. It just creates pods continuously. This is not something that is perfect yet, and there's still a little bit of, still some manual labor involved here, but this is where we're going, and it's going quite well so far. I want to just talk a little bit about how we move those shops from shard to shard. How can we do that with minimal downtime? How can we not punish these shops that are very large? So if we just look at 2 of the data stores here, like Redis and MySQL, we can imagine that we want to move a shop from pod 9 to pod 23. The very naive way of doing that is that you copy the shop by going through every single table, and you find all the records that belong to the shop with a simple query like this. Give me all the orders where the shop ID is this, give me all the products where the shop ID is this, put it into the target shard, and while that is happening, you don't accept any writes. Because the problem is that if you have a shop, and while you're copying that shop, it's inserting a checkout, but you've just copied the checkout table, that checkout is going to be lost. So you need to basically lock the shop while you're copying it. For a small shop, that's not a problem. That may just take a minute, maybe less than a minute, maybe a couple seconds. But for a large shop, this can take a very long time if you don't allow any writes while you're copying it. What we're working on now is not doing this lock, move, unlock, but instead, we look at the MySQL bin log and stream these events as we're copying the shop to avoid locking the shop and having downtime while we're copying it. The bin log is what is in MySQL vocabulary where every modification to the database is logged. So if you change a row, insert a new checkout, it is registered in the bin log as events. Insert a new checkout for this shop, insert a new product for this shop. So what the pod balancer is going to do, and we're starting to work on now, is that the pod balancer is going to stream the bin log and look at new events that are coming in that haven't been copied at the bottom. So the bottom tries to copy all the old data, and the bin log tailor component of the pod balancer is replicating new events. So old at the bottom, new at the top. This means that we don't have to lock the shop for an extended duration of time. Now, when that's done, and we can now imagine this is the discrete moment in time where the shop is completely replicated. For now, we need to move it to the new pod by updating the routing information about it. So first, we lock the shop. No writes can come in. We interrupt all jobs, all web requests that's going on for that shop for a brief couple of seconds. Then we go into a routing data store, the data store that is storing the mapping from shop to pod and from pod to data center, and we update the shop's pod ID in there. Immediately, this is reflected, and things start going to the new pod. We unlock the shop, and the shop has been moved. Then we remove it from the MySQL layer. We move the jobs and other things that are in Redis over as well, which are asynchronous, and now the shop has been completely moved. You multiply this by running 1,000 of these in parallel, and suddenly you can move a lot of shops to a lot of pods very, very rapidly. And you also add on top of this, making really good decisions about which shops you're moving at what time to keep all those shops balanced. So now we've talked a bit about traffic. We've talked a bit about how the application tier works with these pods. Now I want to talk briefly about how we connect these two. How does the traffic layer know how to route the request to the correct pods? For this, we have a very well-named component called Sorting Hat. What Sorting Hat does is that it looks at requests that are coming into the Shopify network and tries to figure out which pod that request belongs to. It needs to go to the region where that pod is active, and it needs to work with things like failovers and shop moves and all of these different components. This is a very, very core part of the podding architecture and one of the first things that we worked on. So, again, we have the traffic layer, and we have another OpenResty Lua module called Sorting Hat. What Sorting Hat does is that it looks at these, it knows which pods are active and which pods are inactive. So in a region, a pod is active or inactive. There's always a hot replica pair so that pod 2 can become active in region A if there's a catastrophe or we need to do some maintenance in that region. And of course, the other way around too. So they're always set up in pairs. Then we have this routing database from before that we use when we move shops around. Sorting Hat is the consumer of that. It is the only thing that queries it and asks about where shops are living. So if you have a customer coming in, getting their products for sneakershop.com, Sorting Hat is going to ask the routing layer to route sneakershop.com. Sneakershop.com is going to return back a shop ID, shop 238. It's on pod 2, and we know that it is active in region B. So Sorting Hat then routes the traffic there. This is very simple. It's, I think, a couple of hundred lines of Lua, querying this data store and doing this thousands and thousands of times a second. This is what ties this whole podding architecture together and makes the traffic layer marry the data and application layer. The last thing I want to talk about is how we fail these regions over, right? We have the active pod and we have the inactive pod. How do we flip them over? And how do we do that with minimal disruption? For this, we have the pod mover. The pod mover moves pods between regions with minimal downtime. We're now at a point where we're getting very, very close to having almost zero downtime regional failovers. This is really important for us because we think this is such a core thing that we want to be able to do all the time. If someone wants to do maintenance in a cloud region without any repercussions, they should be able to move all the pods to another region, do their maintenance, and move them back without any risk. This avoids this problem of having very expensive staging production environments that emulate an entire data center, when instead you can just get really, really good at moving pods between data centers. So what the pod mover does is that if region B is having some kind of incident, it may be out of power, it may be doing maintenance, it may be subject to a hurricane, it may be subject to flooding, whatever happens, we need to be able to move that region over. This is the pod mover's job, and it can do this very, very rapidly. The way the pod mover works is that it goes through a series of steps to fail over a region. The first thing it does is disable cron in both regions, so we're not doing new periodic jobs. The second thing it does is that it goes back to that routing data store, the data store that keeps all the information between shop to pod to region mappings, and where the shop balancer or the pod balancer was looking and modifying the shop to pod mapping, the pod mover is responsible for the pod to region mapping. So it updates it. What happens now at Sorting Hat, that thing that was looking at requests and routing them to the appropriate regions, routes the request to the new target region. We then fail over MySQL to the target region, that little animation that was before. We then enable cron, and we transfer the jobs that have not yet been executed in the source to the target to then be executed later. It's fairly simple at a high level. Of course, there's a lot, the devil is in the detail here, but this is at a high level what happens when we do a pod move. So what about the errors, right? I mentioned that we wanted to minimize the errors. When Sorting Hat starts to route to that inactive region, the database is not yet writable there. If someone is doing a checkout, they're going to have that dreaded experience that everyone in this room has probably tried. You're checking out, and you get an error back when you've just entered your credit card details. And now you have to call someone and ask what's going on. We don't want that scenario, so we sat down and thought about how we could fix this. Again, we took out our hammer and nail, OpenResty, and solved this problem. If you have MySQL replica in two data centers, they can't both be writable at the same time. One will be writable and one will be readable. There will be a couple seconds of downtime where people will have these terrible experiences. But what if you can pause the request at the traffic tier? If you can pause the request while they can't be served in the new region, and you know that they're going to do a write, you can do basically 0 downtime failovers. So the pauser module will pause requests in the middle of failovers to avoid serving errors. So a customer comes in, they're trying to create a new checkout, doing a failover, doing those critical seconds where the database is not yet writable in the new region. So we add them into a queue. We drain that queue from a throttle to avoid too many people coming in at the same time, and the throttle is, of course, disabled while we're failing over the region, and the MySQL has not failed over yet. Then the parser will finally give you an HTTP 200 response later. So this, instead of this giving you this dreaded error page when you've entered in your credit card details, you're just waiting 5 seconds. This works now, and it's in production for us. So this changes the pod mover flow a little bit. All this stuff is the same, but Sorting Hat, when it routes requests to the target region, it inspects the request and makes a good judgment on whether or not this is a request that will perform a write. If it will hold the request back at the low balancing tier. Then it will fail over the MySQL region, resume the request, enable cron, and then transfer the jobs. Really, really simple, and this has gotten us down to very, very few errors doing failovers. We want to be so confident in these failovers that people can just issue a command in Slack and fail over a region. We already have this working, but we're not quite confident enough yet to do it in production pods, but it will be just weeks before we're there. You type in a command, and then you fail over a pod. You don't have to care about the customer disruption because there should be none, and we work as hard as possible to make that true. This is a core primitive of the pod architecture. If there's an incident, someone should just be able to come in, middle of the night, fail over all the pods, and go back to bed. Maybe someday this will be automated, but this is still a tremendous step from where we were years ago. Just the last thing I want to note off on is just another one of the secondary benefits of, second-order benefits of this pods architecture. Right now, we're starting to experimenting more with the cloud, and with this architecture, it's just a matter of putting a couple of clouds or a couple of pods in the cloud. Of course, there's a lot of work going on to get all these stateful tiers and the stateless tiers in the cloud, but when we have it there, we can just gradually move shops there without disrupting the rest of the platform. So we have a little gas pedal where slowly we move shops to the cloud. And as we gain that operational expertise with the cloud, we can move all of Shopify over there. This really marks the end of my talk. I hope you have a pretty good idea now of how Shopify works at a high level, and maybe some of this you can take home and think about. Maybe some of this will be applicable, and especially if you're a SaaS company, a lot of this should be applicable. I've talked about all these components, the pods, the pod balancer, the pod mover, and Sorting Hat. Thank you so much.
Really cool talk. Thank you, Simon. There's also some really good questions. One of them is, I understand how you move pods, but how do you move them if the region is down, unreachable?
Yeah, great question. So, okay, let me go back to this slide because it's quite close here. So the question is, what happens when region B here is on fire? That region is unreachable. How do you fail it over? Well, there's certain things you can't do, but you can do checks, right? So one of the problems would be, well, the database is not completely caught up in the new region. So you have to make a judgment call, right? At this point, the process is still manual, and it will tell you, hey, you're going to lose this much data if you perform this failover. Are you sure you want to do it? So the pod mover is as resilient as possible. Best case, it will do a pod move with all the jobs, all the data moved, but in the case where it can't, it will ask you questions. It will ask you, are you okay with losing this much data? Are you okay with not transferring jobs? And it will still perform the best effort thing that we can do.
Cool. There's a question about, like, it sounds like the pod mover is spawned in multiple instances. How do you avoid race conditions between them? And how do you avoid smaller shops being moved all the time?
Yeah, I think this slide is appropriate to show that. So when we talked about the pod mover, initially what we wanted to do was, well, okay, let's design it so that when you update the routing information, there's a bunch of subscribers. One that's responsible for jobs, one that's responsible for stopping cron, one that's responsible for failing over, one that's responsible for sorting hat. And then they all subscribe to this like kind of pub-sub system. But distributed coordination is very difficult. So we didn't want to do it. It's too complex, and the ROI is just not high enough. So this is literally one script that is running on a machine somewhere, right? And which machine it will run on is, of course, resilient to which regions are down and things like that. But it's one machine doing a bunch of sequential steps. That is resilient, and it's very, very simple.
Yeah, that sounds like how you would avoid that. And then there's another question here. Is the customization of Nginx a task for feature developers or operation?
What feature?
The Nginx task, the OpenResty.
Oh, yeah, okay. So it's primarily been a place where infrastructure engineers have made modifications to the OpenResty layer, but we have had some application engineers and do various modifications. For example, to redirect fractions of traffic and do tests and things like that. So I would say it's probably like 90% infrastructure engineering at this tier and 10% product engineering.
There's also a question about, like, how do you implement multi-tenancy within a pod?
Yeah, okay. This is almost a talk in itself. But sharding is essentially, we shard by the key, so the shop ID, and every time you do a query, you're always in the context of the shop. So you can imagine that if you're doing a web request or a job, you can only query data that is belonging to that shop because every query is appended with the shop ID. So it does like select all from orders where shop ID is this, or select product where ID is this and shop ID is this. So they're all in the same schema. We don't run hundreds or thousands of schemas because that's not a very normal workload for MySQL, and we want the workload to try to be as normalized as possible. That's the very high-level overview. One other thing I'll note is that we do the sharding at the application level. We don't have a proxy or something like that. When we implemented sharding, that's not something we were comfortable with. So it's application-level sharding, sharded at the shop ID key. Schema is shared between the shops on the pod, and every single table has a shop ID key embedded in it so that we can do these queries efficiently.
Really cool. Like, I think one of the two last questions, there's something about really question about, is the Kafka, is it something that would replace MySQL bin log for moving shops?
I'm not entirely sure how to interpret that question, but I'll give it my best. If the question is whether we could put the entire MySQL bin log into Kafka and use that instead, the answer is yes. We currently don't relay the bin log into Kafka. Not sure exactly why. It's not something that we really found a use for. Tailing the bin log works really, really well for us right now. Moving to Kafka, maybe that's something that we would do if there were other use cases for it. But right now, I don't really see the ROI on using Kafka for the bin log as very high.
And I think the last question, somebody asked, are you looking into Kubernetes?
Yes. Like those little cloud regions there on the right, that's Kubernetes.
So it's in production?
Yes.
Okay. Okay, I think that was really give someone a hand, and remember to rate in the app if you think it was good. Also check out Simon's blog. He has a really cool blog where he writes about this, and Google his name and you will find it. It's really good. But give him a hand.
Thank you.